In today's video, we will be discussing Physics 251, Week 6 Video Explainer problem number 61. In this problem, we are tasked with calculating the force that an astronaut exerts on an oscillating spring in space. One thing to note about this problem is that it's actually based on a real-world concept. The concept in question here is the body mass measurement device. This device was developed by Russian scientists in order to weigh their astronauts in space. So I've drawn a little picture of it right here, as you can see. It stands for the BMMD for short, but pretty much what they do is an astronaut will lay on this spring, and the spring is obviously a known spring constant, and the spring is kind of retracted and then released, and as they oscillate up and down, they're able to calculate their weight based on the frequency or the period of oscillation. So let's go ahead and get into the problem. And before I start, if there's anything that seems kind of unfamiliar in this problem, I would recommend going to the Week 6 lecture notes and looking at pages 10 through 14 of the slides. I think that would give you a little better idea of what's going on. So some of the constants in this problem, we have that the mass of the astronaut is 75 kilograms, and we're also given this function right here for the position of the astronaut. So we can remember here that acceleration is equivalent to the second derivative of position. So here we have our little given right here, and we also need to remember Newton's second law, force equals mass times acceleration. Here's just kind of a little diagram I drew to kind of remind us that we can get between acceleration, velocity, and position through derivatives and integrals. So let's get into the problem. So I've started off here by kind of substituting this out, just kind of expanding it a little bit, and then, of course, inputting our equation to take the first derivative of it. And from here on out, I'm going to be referring to this radians per second as just pi. So here we have our first derivative here, calculated at, of course, we're going to bring the 0.3 out, and then take the derivative again. And we can remember that the derivative of sine is cosine. And so we have this equation here. From here, we're going to multiply pi by 0.3 meters, and this is going to give us 0.94 meters per second. And from here, we just need to do some simplification. We remember that the derivative of cosine is negative sine. So plugging back in here, we get 2.96 meters per second squared. From here, we can kind of simplify our equation. We get that the acceleration is equal to negative 2.96 sine times pi times time. So from here, we're just going to be taking, inputting the variables for time, which our t1 is given it 1 second. So inputting that here, the sine of pi is 0, so this just cancels out, and our acceleration is left with 0. From here, we can plug into Newton's second law, and we get that 75 kilograms times 0 meters per second acceleration is 0 newtons. For part B, we're going to be taking, calculating for time 2, which is 1.5 seconds, and doing the same process here, where we get the sine value as negative 1. Solving through, we get 2.96 meters per second squared, and then calculating this based on Newton's second law, we get 222 newtons. I hope you all found this video helpful. Thank you for watching.